Okay. Well, hopefully everyone has been fed and caffeinated and all the like. So I wanted to pick up, there's one spot that's really echoey. I wanted to pick up again from this point about the idea, if this was true, that there was a single rate limiting step, the only information you need to know about how fast a pathway could work is who's the slowest one, and once the identity of who's the slowest changes, then you kind of set a new cap on what's possible. And so I want to first, before we move into kind of the 4 steps and like individually changing an enzyme, and we'll be using the R to simulate this, let's imagine 2 very simple cases first. Let's imagine there's just one enzyme, and as I mentioned before, all of what I'm talking about assumes the concentration of S and the concentration of P are constant. So look at this relationship first on this side. If there's just one enzyme, you have a substrate and it gets turned into a product. And now we're going to put in different levels of enzyme. How will the reaction rate change? What shape will that have? What type of function? Linear, maybe? Anybody else like linear? Anybody ever done an enzyme assay? I've done some. This is exactly an enzyme assay. You have plenty of substrate. You put in 10 microliters of extract, you get a rate. You put in 20 microliters of extract from your cells, and you get twice that rate. And it goes perfectly linearly. Right? And so you get a proportional change in V with that one enzyme. All right. Now, the first somewhat more complicated question. What if all 4 enzymes, like let's say they're all in one operon or something, I could control all of them together, something like that. Right now we've got 4 of them. What if each and every one was going to go up by the same factor? Let's say I double all of them. So let's use the same numbers as before, 3, 1, 5, 7. I'm saying, no, now they're 6, 2, 10, and 14. Oh, and I should explain my axes, sorry. So the 1, like the 1 and the 1 represents kind of like the initial state. So these are relative concentrations and relative flux. So initially, you'll always start there, kind of like where we are. It has a flux of, relative flux of 1 and at a relative level. So now I'm imagining, like I said, like there's one big dimmer switch. I could change all of the enzymes together. What will be the shape of that curve? Will it be flat, curve up, curve down, be linear? Something more exciting? What do you think? That's a really boring answer. Just linear. Who likes the just linear? Actually, I do too. So we'll do this actually in R. It is also just linear. So remarkably, as long as all changed by the same factor, same proportional fold change, it stays linear. All right. Now, bonus question. Hard enough, maybe even Supreet would be challenged by this one. What happens to all of the intermediates? So if you double, let's say you double the enzymes, you've doubled the flux, do the intermediate concentrations double? More than double? Less than double, but increase? Stay the same? Go down by half? Like that's interesting, right? But they're all moving faster, right? So this is a little bit more tricky. So this will be the first thing that we'll do with the tutorial. I think I've got that as the next slide. Yeah. So when we're going to be moving to. Yeah. All right. So. Who has got this set up on their computer? Anybody? Who has R and R Studio set on their computer? All right, so if you don't have a computer or if you don't have it set up, if you can just co-localize with someone who does would probably be the easiest way to do this. We certainly don't all have to do it, but it's good to see it yourself. So the way of modeling these that we're going to do is we're really take it kind of mechanistically in terms of each and every step gets to have all of that, a whole bunch of Michaelis-Menten biochemistry. And at first it may look really super awful. Well, it kind of looks awful even after a while. So those blue arrows represent the net flux. Given what I told you, there's really flux in both directions. But just if there's a net flux going forward, it means the forwards are larger than the reverses, right? And so if we look for any given variable, so we have three variables here, xi, xj, and xk. Those are the variables. Each one of them has their own ODE, right? An ordinary differential equation. And if we were to number these reactions, forward reactions and the reverse reactions, then it means for this guy, we've got 4 different parts, which I believe are reactions 1, 5, 2, and 6, right? They're going to be positive for the arrow coming into xi or the arrow going backwards from xj into xi, because either of those will increase the amount of xi, and they'll be negative for the 2 reactions going out from xi, either going forward onto xj or backwards to s. Sound good? So there's 4 Michaelis-Menten expressions, and each one of them I've broken out the enzyme times its kcats and the other enzyme times its kcats. Does that make sense? All right, and then there are other parts to these models, and I know some of you have probably done substantially more simulation than I have. I know that that's true, and some of you probably have not necessarily done. We also need to define, of course, the time course, and we've got our initial conditions. What is the variable value in the beginning? And as you can play with it if you want to. It turns out the initial conditions don't matter at all in this system. You can set them all as 0, you can set them all really high. Don't put a negative value. A negative concentration really is truly meaningless in reality. That will make things break and go weird. But the system will not otherwise move into bizarre nonlinear behaviors. And make sure, by the way, to use version 1 for now. This is the simple version, it doesn't have as many charts that come afterwards, though the parameters and everything else stay the same. So, with this kind of work, you get to have a lot of parameters. And they come in different types. We have all of the different Michaelis constants. So these would be the concentration at which each of those different reactions forward or reverse would be half saturated. We have all of the different kcats, the maximum speed the enzyme can work in the forward or in the reverse direction for each of the different enzymes. We have the enzyme concentrations and then the substrate and product concentrations. Now, I made those pretty long for a reason, is that we want to change some things dynamically. And so these are relatively simply set up that it starts out at 1, like relative level of 1, like say up to time 40. If you want between time 40 and time 60 to double it, you just set that next number to 2, and then it can go back to 1, things like that. So we can have like enzyme concentrations kind of stepwise change through time, and we can see, well, what happens, all right? And to run the program, if you're not familiar with it, there's a variety of ways you could do it. You can do, either Control or Apple A to select all, and then there's a little Run button in Run Studio. If you're not familiar, probably in this room, you can find someone quite close to you who is familiar with how to do that. All right, so let's do this. So taking this first model, let's try this doubling everything. So use like that second time period, and we want to change that number 1 to 2 for each of the enzymes. So there'll be a period of time that all of them are going to be doubled, and then they're going to all be cut back in half back to the original amount, right? And then we can see what happens. And then I've got plotted out the concentrations through time, the actual variables, as well as the fluxes. So there's one part of the code I didn't show it here explicitly, where it calculates then what all the fluxes are, saves that, so that you can actually plot what the flux values are with time. All right? So let's try to do this over the next couple minutes. If you have a question, ask me, and then let's see what we see. Does that make sense? Okay. Anybody have a question? I'm happy to pop up individually, or you can ask me generally. But keep in mind your guess, what you thought was going to happen. We already answered it for flux. Flux is going to double. But what's going to happen with the rest? With the concentrations? What do we see? Yes, I think if it's version 1, there should just be 2 plots. One of them, the first one is xi, xj, xk through time. So it's just the concentrations of the substrates.
Okay.
And what you should see, I think, is they start at some value. Within the very first few time steps, they come down to something, and then, yeah. So this system is really boring. It doesn't oscillate or do anything. This actually is quite true of metabolic systems in general. A series of catalysts, for reasons that we'll describe, will tend to have actually very steady behavior if you're not, like, say, oscillating the level of an enzyme or something. Yeah. And then the flux values, as you see, also pretty quickly come to something. Yeah. And then the question is, what happens? Like,
flux is like also flux is the errors, right? Like.
Yes. So what I've got labeled in there is VA, VB, VC, VD, and actually, yeah. So this one's orange, red, blue, if I remember correctly, and black. Right, so you've got the 4 different fluxes. And so do people see this? That after a very short period of time when they start off at different values, pretty soon you only see one color. Why do you only see one color? Because they're the same value, right? This system comes to steady state really quickly. Yes? But then what happens during that time step when the enzymes are set to twice their level? So between time 40 and time 60. Do you see the... Well, let's start with the fluxes. Are the fluxes behaved? Does it just step from wherever it is to twice that high and then back? It should, and with no weird, it's instantaneous. You change the parameter, and there's no transition time. It's just immediately everything goes twice as fast. Yeah? What happened with the concentrations? I promise the plot's not broken. What happened to the concentrations at time 40? Or time 60? In the first plot? The concentrations are the x's, xi, xj, xk. They don't change at all. So it's kind of remarkable. If you were just measuring metabolite concentrations, you'd have no idea that things are happening twice as fast. It's like if you had a section of road, over 100 meters, and there's 15 cars there. They could be 15 cars parked, or 15 cars that are all going at 100 kilometers an hour. It's still just 15 cars, right? There's no difference in the concentrations because it's been absolutely, every single rate in and out has been doubled. So I actually think it's kind of cool. It's not, at first it's not necessarily intuitive. All right, so before I go on, I just want to make sure. Does everybody have this working? Or I guess I should say, if it's not working, like I said, find someone who is, but it sounds, hopefully everything is hunky-dory. Okay. Yeah, we already talked about that. All right. So, for this exact system, we had before where I laid out those kind of Vmaxes as 3, 1, 5, 7, and everybody thought the second one was clearly going to be the problem because it had a Vmax of 1. Here's a little bit more information, right? Now we've got K-cats forwards and K-cats reverses and Kms, etc. All right. Who's the rate limiting one? Right? Yeah, what should I be doing when I look at those numbers to figure out which one might have the most control over setting the pace, or be the only one in control? What's that?
Lowest value.
So you can think of the lowest value. So we have two of them who their forward, three of them, the forward values are 15. So which one of those? The lowest what? The lowest reverse value. Yeah, so perhaps enzyme D with the lowest reverse value, maybe. It also has relatively low Km. Some of the other Km values are a little bit different, right? But it's not very obvious, right? It's not clear here what that should look like. All right. So, I don't want to do this. So so do people have a guess, right, between A, B, C, and D that you think might be rate limiting? And so what I want you to do is set your other value, set 3 of the enzymes back to 1 and leave the one that you think is most important at 2. And if the idea of a rate limiting enzyme is true, everyone who guesses wrong, it won't matter if you double the enzyme because it's not rate limiting. And it'll only be those who chose the right answer will see something happen. Yeah? Does that make sense? So what I want you to do is take those 4 enzymes that between time 40 and 60, you said it's 2, put 3 of those back to 1, and pick one that you want to test. Has anybody tried something and think they're the winner? Did they guess one correct? Well, if you increase the enzyme, and if you pick the right one, you should see the flux go up. Did you see flux go up?
For all of them?
No, not the all case. Like I said, set 3 of them back down.
But the flux should go up for all of them.
All fluxes should go up if it's going to reach a new steady state, correct. So did you try that?
Yes.
Which one did you try?
D.
D. Did it work?
Yes.
Oh, okay. So he thinks D is going to have an impact. All right. So we had enzyme D. Anybody else try D? Is he the only one who got any changes? Anybody try C? Yes? Sorry, I couldn't quite hear. The flux went down? What did you set it to? So it's at 2. Or 1, and on the second chart, the fluxes went down? It went up. He disagrees with you. He thinks enzyme C is the one that matters. Anybody try B? Nobody tried B. Anybody try A? You tried A? Did A make an effect? All right, she thinks both of you are wrong. Will somebody try B? You can probably guess already from my tone, right? B is going to have an effect too. This seems very problematic from the way we were looking at the world, right? There is not a single step that is the only one that matters. Now also, here, you all doubled it. Did any of you see the flux double? How much did the flux go up? Yes, the magnitude definitely varies. Like, approximately, how much did you see flux go up?
So for D, it went up more than it did.
Yes, yeah, but how much for D, you think? 1.5. Why not 2? If it's such a good enzyme.
It could be 2, but
No, you're right. You're right. It's more like 0.5. What did you see for B?
it's like 0.1.
Yeah, maybe 10% or something, right? So all of them matter, yet none of them give you like the full twofold effect, right? That seems problematic. So we have a way that we can look at this kind of all at once in a more systematic fashion. So pull up this script. This one, this MCA-V versus E, it's running a loop, and it is going to test many values of A and B and C and D, store those fluxes, and then we're going to plot those flux values versus all the different enzyme values, exactly what the charts that I've been making. All right, and then you can see kind of systematically what this looks like. All right? So while you're pulling that up and getting it in front of you, I'll draw, if I can remember which one's which, in terms of the orange or the red is the highest. Well, I'm not going to worry about being precise about that. What you'll see is a picture where each of the colors looks something like that. Does that look about right? I just couldn't remember whether red and orange is on the top and black or blue is on the bottom. I knew they were split that way. Okay. So each of these curves, to be clear, this is a very, very important point. That V is the steady state V across the entire system, where VA equals VB equals VC equals VD, right? Like they quickly come to match each other. Each one on the x-axis is only changing one of the enzymes. So when we look at, like when you look at your red curve, it's only changing the red enzyme and all the others being held still. So you're just changing that one. Or hold the other one still and just change the blue, right? And you should see this sort of shape. And so this kind of looks like our initial intuition of rate limitation, but it's just much more analog and it's spread. Every enzyme matters, right? It's kind of not surprising. Any one of them individually, as you begin to get close to very little enzyme, will eventually bring this thing to a halt, right? Like that's kind of obvious. Any of them, as you go to really high levels, just can't make the system possibly go any faster. But they have differential sensitivity. The system has differential sensitivity to each of these. And there's a way that we talk about that. So we can look at the slope right at their current value, and the relative change in flux per relative change in enzyme, we call this the control coefficient for that enzyme. All right, and all of this, by the way, we're using simulations and R and things like that. In the early 1970s, this may shock you, but they didn't have MacBooks, and they didn't have RStudio or things like that. This would have actually been a real pain in the butt to do. And so instead, they did more like the beautiful, elegant stuff that Lindy talks about. They came up with an analytical solution. Now, they didn't have, these are awful. You saw those ODEs. Do you want to find an analytical solution, in Maple or something for them? Like, no, this is awful. And so instead, they linearized around that space. They basically ignored everything else, but just if you make local changes, let's just pretend that it's a straight line and they don't always have this downward curvature, linearize this, and a lot of what I'm talking about in the basic messages come actually from the early 70s. And this is an area of theory called metabolic control analysis. MCA. All right? Now, probably one of the most beautiful, lovely things to emerge from having done so is there is a really cool property about these control coefficients. There's something that is always, always, always true. Does not matter how many enzymes, what the topology of the system is, anything. What are those values going to be, and what do they add up to? When there was one enzyme, what was the slope of that line? 1. Remarkably, the sum of the control coefficients, and it doesn't matter how many you have, is also always 1. Always. Any system, selected for, not selected for, anything, you cannot make a system where that's not true. That's the summation theorem. The sum of all the control coefficients is exactly unity. It's one of those just really kind of wonderful, neat results. Think about when we did this, when we changed all of them. We hadn't yet gotten to this idea that, well, some might matter more than others, but if they all sum to 1 and I change all of them, it doesn't matter. Like, it's like you could imagine those 4 enzymes are just one big enzyme that takes substrate all the way to product. Who cares that there's intermediates in between, as long as the catalysis rate of all steps, somewhere in there you've got all the control you need to double the rate. But it's just if you break it out one at a time, they're going to have different values. They're all going to matter at least some, but they will always total up to 1. And there's a neat kind of thing that comes then from this. What would be the average control coefficient in a cell? So here, what's the average control coefficient for our system? If they sum to 1, and we have 4, this is really difficult math, I know. 1/4, right? Okay, fine. How many enzymes are operating in an E. coli cell or yeast cell or something at once? About order of magnitude, right? This is pseudo-physics-y. What order of magnitude? Not enzyme molecules. How many separate enzymatic steps? 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5. I promise it's on my hand. Sadly, which finger is it? No, there's more than 100 different enzymes. 10 to the 3, yeah. It's usually between 500 to maybe 1,200. It depends upon, exact details. But it means that this is going to be the sum of the control coefficients over the number of enzymes, which is just 1 over, about 1,000. It's very tiny. Most enzymes, even if they're absolutely essential genes, and if you mutated it and it was homozygous, you would be dead, most of their control coefficients are very, very small. And let's imagine a couple steps have relatively big control coefficients. Like maybe 2 of them sum up to 0.5, then the remaining 0.5 is spread amongst the other 998. So no matter what, you're stuck with a scenario that most control coefficients are very small. And that's just the way it is. There's no way to get around that. Yeah? What's that? Oh, it can be all over the place. You can definitely have steps. It depends on what the conditions are. If you grow in a chemostat where they're nutrient limited, the uptake enzyme, so as to say the transporter, can often have a very large control coefficient, 0.5 or something, or more, and thus everything downstream is just very, very tiny. Now I'll say, things do get a little bit more funky, where you have branch points, and in metabolism you do. So the summation theorem is still true. However, you can actually have ultra sensitivity. You can have a single control coefficient have a value greater than 1. Wait, I just told you that's not possible. How could that be possible? If one enzymatic path is kind of stealing an intermediate from some other path that also needs to occur. So if I were to turn it up, Like maybe one of them, the one that's kind of being stolen from, if I turn it up even a little, it makes a really large effect, more than proportional. What would that have to be? What would that have to say about the other control coefficient? It has to sum to 1, and I just told you one of them, say, has a value of 1.2. Negative. You can actually have enzymes for purely catalytic reasons. If you turn them down, it would go faster. Right, so, right, we're not going to go. It is entirely possible. On a linear pathway, they're bounded 0 to 1. The summation theorem will still be true no matter what your topology is. However, it can get funky and you can have ultrasensitivity to negatives and, yeah, but it's still going to sum to 1. All right, so what actually happens then when we change an enzyme, right? And you guys saw this. Here was changing, I think this is enzyme B, if I remember correctly. There are kind of a couple things that happen as it's being, it goes from 1x, 2x, and back to 1x strength. What are those things? There's a little bit of concentration changes, and that will be critical. And look what's happening with flux. Kind of interesting. Look at your very first blue dot there, for example. Approximately how much higher than the line, its original line, is it? It's about 2-fold. Instantaneously, because none of the concentrations have yet changed, you've doubled that flux. It doesn't last very long, right? Back down. Same thing, when you cut it, it'll immediately drop to half and then pop back up. But you're not changing, that's after you've already made the enzymatic change. Question? There's very little for that enzyme itself. It turns out for the other enzymes, yes, there's a lag. Yeah, because it has to propagate through. Yeah, absolutely. And this is the same chart, just zoomed in on just a little tiny stretch of time. So you can see the other ones, there is a little bit of a lag to come up to speed. So now everybody's going 5% faster or something like that. But this one started off 2-fold faster, the amount you changed it, but then quickly, it shuts back down. And it's not because of allosteric regulation or anything like that. That doesn't exist in the system. I mean, you could add it, you can model that, but that's not what's here. A quick drop. All right. So why so little effect? Why did you only get, you doubled the enzyme, why do you only get this 5% effect? That seems really depressing. And that's with only 4 enzymes. Any thoughts? What is it? Well, they are coming and going away, but I would say you're on the right track. There's not infinite accumulation. It does reach a new steady state, but as we saw from the concentrations, they shift a little, right? So the second thing is that we'll talk about the shift in concentrations. And unfortunately, shifts in exactly against the enzyme. But there's another thing. Kind of goes back to when I first started talking about metabolism and the fact that these are reversible reactions. Part of the reason why you don't, it's a little bit less impressive than you might think, is you doubled both the forward and the reverse. And so you're just working against yourself twice as hard as before, and you're pushing forward twice as hard as before. So yeah, the net difference is a bit of an increase, but it's much less than one would think. Right? And so because of this, if you remember, we had like the net reaction was, if we factor out the enzyme, so like we pull one of these enzymes out, then it would be, kcat times the saturation term minus kcat reverse times its saturation term. Unfortunately, this gets doubled for both. And indeed, like as in this example drawn up here, here's like a textbook example of what a steady state pathway might look like. And the important thing for it to be steady state is that the net rate, the differences have to be equal to each other. If the difference between the forward and the reverse has to always be 10, in this case, to have a steady state of 10. If it's 10 and then 11, you're not at a steady state yet. Something's going to be building up, right? They all have to equal each other in terms of their differences. But it doesn't mean that the ratios have to be the same. For that first reaction, there's a 10,000 to 1 ratio going forward. Awesome. How nice and efficient. That's great. Look at this last one. That sucks, right? 500 going forward, 490 going backwards. It's like Sisyphus pushing a rock up the hill and barely ever making it. Like, it's just a lot of forward and back and forward and back. And so that's one of the main reasons why things, aren't as responsive as one might think. But then the second aspect is this change in saturation. So like our model, we've got this kind of thought experiment scenario of this instantaneous doubling. So if we have the 3, 1, 5, 7 suddenly going to, not all of them, come back. So we're going to double one of them. We'll pick on enzyme B again. If we had the original, so the relative flux, where I'm just going to define that as 1 starting off, and the relative concentrations. Okay, where everything's at a steady state, and we're going to double one of these enzymes. What happens, as we just saw, the instant after change? Right? Instantaneously, that hasn't changed, that hasn't changed, that hasn't changed, but enzyme B doubles. The moment because you haven't changed anything else. So far, and this gets to that lag concept, these concentrations are still the same. So just that very first moment, that flux will be double. But then what starts to happen? Is that a steady state? Right? Is this a steady state? No. This is happening twice as fast. So it's outrunning this one, and it's overrunning that one. So what's going to start to happen, right? Now, it's going to cause this guy to build up, and that guy to be drawn down. Okay, what are the consequences of that? On its own enzyme, it now has less substrate compared to, and more product. Given that it can go in both directions, it's going to start to sink. What about the enzymes forward and, past it or before it? If you now, from the point of view of enzyme A, tilt to having relatively less product, it can flow a little faster. So enzyme A can begin to work faster. What about enzyme C? It's now got relatively more substrate compared to product. Same thing, it can go up, but if it's up, it's no longer in steady state with enzyme D. It's going to also have to go up. This is also going to rise. Everything is going to start to shift. It will come to a new steady state. So imagine, all of these fluxes are now a little bit bigger at this new steady state. It was, for a moment, you had a nice big fat flux there for B. They're back to steady state. Maybe, it's 1.2 or something like that down the line. But for the concentrations, maybe now the concentrations compared to before might be something like this. Does that make sense? So it will find itself, like it has to find itself naturally back to a steady state. This is not an evolved property. You can just throw some random catalyst into a tube, and this will have to happen. Unless it just, unless we've got like irreversibilities or things like that, where there is no counter force. But as long as things are reversible, which is certainly the majority of reactions, this will tend to hold true. And thus, if you looked, like if I showed you the fluxes after a change and asked which enzyme did I manipulate, who knows, right? What if I show you the concentrations? You'd actually know. So the interesting thing is, even though the flux might be relatively insensitive, the concentrations actually will change. Wherever there's a break point between the things that went down and the things that went up, that's the point that got changed. Now, of course, in reality, you could have whole operons going up and down, and there might be multiple enzymes that change, and so it's not as simple necessarily as just one, but the same concept holds. And so if we look at this in terms of concentrations then, so this is now same x-axis as before, relative levels of just changing one enzyme. But now the y-axis is the concentration of each intermediate. And you can see that as you dial things up or down, some of the concentrations will go up, some will go down, and just depends upon where you are in the chain. Like for enzyme B, this panel here, is it labeled? I can't remember. Yeah, enzyme B. Here it was where it started at a relative level of 1. If you turn it down, its own substrate will build up and the things below it will go down. If you turn it up, its own substrate goes down and its products build up, right? And the opposite happens for the things downstream of it. So let's see if I can hit. So we did. I'm going to skip this for a second and let's talk about this one as the last point. What happens to the control coefficients if I change one of the steps? Right? So we have this idea now that all steps matter, but to varying degrees. Now you do something, you increase one. You're going faster. Okay, yeah, or less, yeah. What's going to happen to the control coefficients? Will they change? Will they stay the same? Something's got to change probably, right? So let's run this, and we'll do this as the last thing and talk about it. So in this V versus E file, run it with the original values. You guys already did that, right? And you saw kind of what the control coefficients look like. Now, pick an enzyme, doesn't matter which one. Let's make this dramatic. Increase it by 5-fold, 10-fold, something like that. And what does the picture now look like? What happened to the curve for that enzyme? What happened to the curves for the others? What happened to the total flux? All right? This is now asking, if I change one enzyme, how much will that affect other future changes in enzymes? Epistasis, right? You can predict epistasis in metabolic pathways from first principles because of this sort of interaction. Any questions on what it is that you're supposed to be doing? Pick an enzyme, doesn't matter which one, crank it, and let's see what changes. They don't all go, I forgot, sorry, little devil in the detail, sorry. Please change the 2 kcat values and not the enzyme, because otherwise that happens. Because unfortunately the way it's being, yeah. Yes, thank you. Change both kcat values, the kcat forward and the kcat reverse by the same fold. So if your enzyme was 15 and 5, change it to like 150 and 50, like 10-fold increase or something like that of both values. So it represents kind of a 10-fold total increase. Then they plot better. I forgot about that fact. Thank you. Which is flat?
On increasing limits, I guess any enzyme is
So you're saying compared to before, the enzyme that you increased, it's steeper now or less steep?
less steep.
Less steep, right? However proportionally rate limiting it was before, you've already made it somewhat better. It's less rate limiting than it was, right? I mean, the concept of rate limiting is fine. It's just, it's not, don't fill in the numbers 0 and 1. that you either are or aren't. You can be more or less. That's what the control coefficient says. So you should see, I do not know what that is, something that looks like this. Weird. I can't even erase it. Right, where this is changing, which one would this be? This would be enzyme C. Let me make it red. So I increased enzyme C in this case, and you can see that the steepness for C has actually dropped. It's relatively more flat. It was the most important enzyme. It had the biggest control coefficient. Now it doesn't. Why is the whole thing shifted? Why is the point now through there instead of down there? Yeah, by increasing C, the whole thing goes faster, right? So now you have a new set point. This is the new normal. But now compared to this new normal, which has the most relative impact, right? And it's changed. It's no longer as important. It's still number 2, hasn't dropped more, but it's not the number 1 most important thing. By extension, what happened to the other curves? They will all increase. They will not all increase like linearly or anything simple. This is, even though it doesn't have odd behavior, this is a nonlinear dynamical system. It's not going to just change in some totally simplified linear way, but all the others will go up. So what does that mean? If I had 2 successive mutations in the same enzyme, each one independently doubles its activity. I'll get some proportional benefit the first time. The second time I do a similar change, will I get the same selective coefficient? No, it's going to go down. Even though I proportionally change the enzyme in a nice, multiplicative way. If I go from 1x to 2x, I'd get a change. But if I now go from like 2x to 4x, I actually don't get as much, even though it's a larger change in enzyme. Right? Even though the proportional amount was still a doubling of enzyme, I don't get as much bang for the buck anymore. Right? And so multiple mutations in the same enzyme, you're going to see diminishing returns. So we've got a lot here, and then I'm off the stage. So CI of changed, enzyme goes down, rest up to still add to 1. And multiple mutations to same enzyme, you get diminishing returns for beneficial mutations. What about deleterious? What if we had 2 mutations, one that makes it have half the activity, and then the other that drops it another half down to a quarter? It's more severe, right? It's the same curvature, right? Because of the curvature it has, as you're moving up, you get less effect than you think. As you move down, you actually get increasing effect. Does that make sense? So deleterious would behave exactly the opposite. All right, let's leave it there. We will do one more exercise with computers for the next lecture, but I've made fairly good progress on that. Thank you very much, but I want to get off the stage to hear research talk.